Hi, everybody. This is Dr. Nigro with a Chem Calculations screencast. This screencast is going to focus on the spectroscopic technique that utilizes UV visible radiation, also known as UV-Vis spectroscopy. If you have questions about general spectroscopy or IR, mass spec, or PES spectroscopy, please look at those individual screencasts. This one will focus just on UV-Vis. Okay, so let's start with this spectroscopic technique compared to IR. All right, so here, the energy of the radiation is greater than what we see in IR spectroscopy. All right, we're really moving, I mean, generally speaking, from around 200 nanometers. And sometimes it goes all the way up to 800. Oops, not up, down, nanometers, which is closer to the IR range. All right. Some techniques focus on far UV, so they can go up a little bit higher. Some focus on near IR, so they go a little bit lower. There's no hard and fast set of wavelengths that define each technique. There's going to be overlap amongst these different techniques. So don't get bogged down in the idea that there are hard and fast beginnings and ends. Just keep in mind, UV-Vis spectroscopy tends to focus on wavelengths between the UV region through the visible region, but that doesn't mean we can't go a little bit outside of those. All right, so what is that energy used to do? So the energy is used by our atoms and molecules to promote electrons to their excited states. All right. And what that looked like depends on the element, right? You can imagine that an element with more protons in its central nucleus may be harder to move its electrons around compared to something with less protons, or something with more principal shells, more electronic shells might be easier to move some of those outer electrons compared to something with less. So there's going to be some difference in the energy required to promote these electrons from their ground state to their excited state. All right. As we know from the quantum mechanical model of the atom, there's a lot of variation in the energy requirements for these transitions. So you can appreciate that you're going to be scanning a lot of this region to find where these transitions are for these different elements. All right. In addition, it also matters what is around it. So the bonding environment around these atoms. All right. We didn't really get too far into that when we talked about the quantum mechanical, the model or bonding, but it does impact some of these. Hybridization has an impact on transitions. You know, polarity can have an impact on transitions. So everything matters when it comes to what causes what, sorry, everything matters when it comes to the energy required to make these transition happen. And so with that in mind, when we see where these transitions happen, that can give us some information about the molecule itself. All right, so what do we use UV-Vis? So we use it a lot to determine, oops, the concentration of compounds within a sample. And the other thing, well, there's many things, but to ID the presence of certain, oops, molecules and elements. All right, now, when I was working as part of my grad school work, I worked with proteins that contain an iron group and a heme group. And that iron had a very specific electron transition that was very easy to spot with UV-Vis. So we used UV-Vis spectroscopy a lot to determine whether that iron was present within our sample. And then we used it to determine the concentration of that particular component. We also utilized it because that iron would interact with different amino acids within my polypeptide, within my protein. I could change what those interactions were, and that would move my transition around. So I could use UV-Vis to see what was attached to the iron as well. So it was a very cool technique for that type of stuff. All right. Um, General setup, just like we saw before. Whoops. We need a light source. All right. Again, that light source can be all wavelengths or specific. All right, we're going to have a lens that's going to allow us to focus that light. We're going to push it through a grating. All right. And then that grating is going to separate it into its wavelengths. And then the selector allows us to focus in on the UV-Vis region of that sample. All right. As it comes out, we have the initial intensity of that light, and then we're going to measure the amount that gets transmitted through, which will be detected by our detector. And now we're going to produce an absorption spectrum. So that's going to be a little different than IR. IR produces what's called a transmission spectrum, where you have 100% transmission. Then you have the valleys showing where light was not transmitted at a particular frequency or wavelength. Here, it's going to be the opposite. We're going to have an absorption spectrum that will show what did get transmitted. All right. This is an example of a UV-Vis spectrum. This is a scan of all wavelengths to measure absorption at, oops, at a variety of those wavelengths. All right, so we're not looking at one single wavelength, we're scanning. In this case, the scan runs for 400 to 750 nanometers, which is right there inside our visible region, a little bit of UV in there. All right, what we see here is a spectrum that's got multiple peaks. All right, we call these peaks lambda max values, and they are for a specific electron transition. All right. You can see this max. There's a second one here. There's one here. All right. And each one of those are going to be for a specific movement of an electron between energy levels. Now, as we know, as the wavelength increases, the energy of that radiation decreases. All right. So that means each lambda max has a, not has, maybe represents would be better, a different energy transition. All right, so because this lambda max is at a higher wavelength, it's going to have a lower energy for its transition compared to this one, which will have a lower one compared to this one. All right, so that's just something to keep in mind, is that those lambda max values are equated to a wavelength, which in turn equates to an energy value. All right, now, when we have these absorbance versus wavelength plots, we're really using it to find the lambda max for the sample. All right. We can use that lambda max as an indicator of a particular element. You know, as I mentioned before, iron has a very specific lambda max when it is present as part of a heme inside of a protein, as do cobalts, molybdenum, chromium. They all have different lambda max values because their atoms are different. They have different protons, they have different electrons, and depending on their bonding environment, things are different. So you can use those as a way to identify the lambda max, which is in turn can help ID atoms within. All right. Once you know that lambda max, you tend to then plot absorbance versus the concentration of your sample using a slightly different technique, still UV-Vis, All right. But instead of scanning all the wavelengths, we're going to choose one wavelength where lambda max occurs. And then we're going to focus our grading on that one wavelength. And then we will switch out our samples of varying concentration. So this idea of producing a plot of absorbance versus concentration falls into what's called the Beer-Lambert law. All right. So this law describes the relationships among absorbance, concentration, path length, and something new for us, something called the molar extinction coefficient. All right. Now, the way this particular experiment works is the first thing you have to do is build what's called a standard curve. All right, that standard curve, you're going to have a set number of samples where you know the concentration. You build them yourself. And then you measure the absorbance at that particular concentration. All right. You should get a straight line that looks like this, which means that that is related to the formula of a straight line, which we know is y equals m times x plus b. All right. Now the y-intercept, all right, if you think about it, if you have zero concentration, you should have zero absorbance. So the y-intercept should be zero. All right, now to replace, the absorbance for us is on the y-axis, the slope of that substance, and then the concentration is on the x-axis. So we get a formula for our line that looks something like this. Absorbance equals the slope times the concentration. So then the question becomes, well, what is the slope? All right. Well, the slope is going to be equal to that molar extinction coefficient times the path length. I don't love that they use, oh, I'll use L. All right. Now the path length is of the cuvette. All right. So over here, you can see here would be our path length. All right. Now most cuvettes that we use in the lab are going to be 1 centimeter, which makes it super easy when you talk about that slope because you just take the one out. All right. Which means the slope really is equal to your molar extinction coefficient. All right. And that is Beer's law right here. Absorbance, which is y, is equal to E times C, or sorry, E times L, which is your slope, times the concentration of your substance. All right. So what is that extinction coefficient? It's a physical property, which means it is unique to each element of a molecule. All right. And it does not vary within an experiment unless your sample undergoes a chemical change. All right, so generally speaking, the extinct coefficient is going to remain constant. All right, so we can do a couple things here. First, we can build our standard curve as shown in this plot. We can use that standard curve and our plotting software to find that slope. And if we know that this is 1 centimeter, then we can figure out what the extinction coefficient is for our particular sample. All right. Now, because this is a physical property, you can sometimes then use that extinction coefficient to limit what your sample might be if you're trying to identify it. All right. The other thing that you can do is once you know what that extinction coefficient is, then you can have an unknown sample. All right. So let's say we ran a reaction and it produced this particular molecule, but we don't know how much of it was produced. We can take that sample, we can measure its absorbance. Let's say it measures right around here. All right, so we can use that. And then we can either come down here right on the plot, or we can take that absorbance value and plug it right into our formula for the line, plugging in the extinction coefficient that we determined from the standard and solving for the concentration. All right. And that is what Beer's law does for us. It allows us to either determine the concentration of an unknown sample based on its absorbance, or if we know the concentration, we can predict what the absorbance should be for that particular sample. But before you can do any of that, you have to build the standard curve so that you can figure out what the extinction coefficient is for your particular molecule. All right. So the Beer-Lambert law, again, is this relationship between absorbance, concentration, extinction coefficient, and your path length. With that, just build a standard curve, determine the best line fit formula, use that to find the extinction coefficient. And then from there, you can do a multitude of things with it. All right. So we've got a problem down here that we're going to look at. All right, the UV visible spectrum of a mixture of reaction components is shown to the right. What is the maximum wavelength for each component? All right, so lambda max for what's that first one? HPR plus. All right, so if I look, its lambda max is right around here, 425. I'm going to say that's right around 440 nanometers. It might be closer to 430, but it's in there. All right. And then lambda max for, what's this, PR? Oops. All right. So we come over here and we look. This one's a little past 550. So maybe 555 nanometers will be the lambda max there. All right. So you can tell that the energy required for the transition for PR is less than the energy required for the transition for HPR plus because it is a higher wavelength. All right, if you wanted to investigate the presence of PR, which wavelength would you monitor? All right, I would monitor 555 nanometers because this wavelength is oh, this wavelength shows the maximum absorbance for the ER molecule. All right, it wouldn't make any sense to monitor down here for PR because it doesn't have maximum absorbance there. Any absorbance you see there is going to be due to the other molecule, the HPR plus. So you want to choose the lambda max that matches your target molecule. All right. You conduct a series of experiments with varying concentrations of Br and build the plot of absorbance versus concentration. Based on the best fit line, what is the approximate absorbance of a solution containing 0.5 times 10 to the negative fifth molar PR? All right. So if I look, this particular plot runs from 0 to 3 times 10 to the negative fifth in terms of concentration. All right. So this amount is here, right there. All right, so I can use the graph as is to determine that absorbance value. And if I look, the absorbance should be around zero point 0.2 based on the plot. All right, based on the best fit line was the approximate concentration of PR in a solution with an absorbance of 1.5. All right, well, if I look, my absorbance goes from 0 to 1.2. All right, so this is off the plot. So this is where I need to use the Beer-Lambert law. All right, so A equals E CL. All right, so I need this, whoops, I need this number. All right, so I'm going to need to find the slope. All right, so the slope of any line is going to be equal to the change in the y divided by the change in x. So I'm going to need to find 2 points that are pretty easy to read. I'm going to go with this one and this one on that line because those look pretty straightforward. All right, so the y is absorbance. So this looks like 1.0, and then down here 0.2. So there's my absorbance values, and my concentration values. That's going to be 2.5 times 10 to the negative fifth minus 1.5 times 10 to the negative fifth. All right, I'm going to plug all that in, and I should get, oops, calculate something different earlier. Let's see. So I'm going to have 0.8 divided by 1.0 times 10 to the negative fifth. Right, one, you doing that right? 2.5. Oh, I did this wrong. Should be one. Sorry. So zero point 0.8 divided by 1.5 to the negative fifth. And I get 5.3333 for my slope. All right, now, if we're working on this in the lab, you should be using a spectrometer. All right, that spectrometer is either going to build the plot for you and then give you the slope, or you can take your data, put it into a graphing program, and build the slope that way. This way is a little hinky because I could be reading it slightly off. And so your slope may be a little different than mine, but for now, I'm going to go with this as my slope. All right, so then I come back to the Beer-Lambert law. All right, so the absorbance I have is 1.5. The extinction coefficient is 5.3333. All right, my path length is 1 centimeter, and then my concentration is my unknown. All right, so I'm going to divide, and I find that my concentration at this spot is 2.8 times 10 to the negative fifth molar. All right, and if I think about it, so 1.5 should be up here. Yeah, see, I definitely have a problem, right? Because the 2.8 is still on this plot. So something is wrong with my slope. So let's go back and look at my slope. See, this is why we do things together. All right, you know what? I think I'm going to swap this point because I think this is where my problem is. I'm going to go with this guy right here. That looks a little easier to read. So that's going to change this to 0.8 for that. And this will just be 2. All right, then my second point is zero point 0.4. Oh, there's my problem. Even with my first one, I had 0.2 there. It's 0.4. That's my problem. But since we're fixing it, we might as well just do it. All right, so we're going to have 0.4 up top, 1 on the bottom. And this is going to now be, oh yeah, that's a big difference. Now it's 40,000 for that slope. That is a big difference. That's my problem. All right, and so we divide 1.5 by 40,000, and we get 3.8 times 10 to the negative fifth molar. Now that makes a whole lot more sense, all right, because the absorbance is higher than my maximum on my plot, and my concentration value should be higher than my maximum concentration of 3. And so now this makes a lot more sense. So this is actually a good place to mention that when you're working these problems, you need to use the graphs that you are given to determine whether your answer is reasonable. All right. You will catch a lot of errors if you do exactly what I just did, where you look at it and you're like, well, that doesn't make any sense. So I must have calculated my slope wrong. Go back and fix it, recalculate that concentration, and now it's correct and is reasonable. All right. So again, UV-Vis looks at the interaction of ultraviolet and visible light with our molecules and atoms. It can promote electrons within those atoms to their excited state. And when that happens, the energy that they absorb is removed from the spectrum. All right. So the light source can be any wavelength or all. You're going to focus it on that UV-Vis region and produce that absorption spectrum. All right. You can either do a scan of all wavelengths and measure your lambda max. Then you're going to take that maximum absorbance and use it to build your standard curve, which you can then use to determine the concentration of an unknown substance or the absorption of that unknown substance using Beer's law, which is the absorbance equals the extinction coefficient times the path length times the concentration of that substance. Okay?